Chapter 3.4, Concavity and the Second Derivative Test, Day 2. Now remember, concavity is how the first derivative changes. It's either increasing or decreasing. And what it affects on the graph is the curve. Something that's concave up, curves like that. We say concave up like a cup. If it's concave down, the second derivative is negative and it looks concave down. It's an upside down cup. Concave down like a frown. All right? And so we're going to start by listing the intervals of concavity, which is our second derivative. So we're going to need to find our first derivative. Let's rewrite this as x squared plus 1 to the 1/2. We'll find our first derivative. So we'll have 1/2 x squared plus 1 to the negative 1/2 times 2x. Clean that up a little bit. Can take the 2 times the 1/2. Those will simplify. We'll have x times x squared plus 1 to the negative 1/2. All right? And then we'll take the derivative of that. And that is a product rule because there's a multiplication of functions there. The first function times the derivative of the second. So that'll be negative 1/2 times x squared plus 1 to the negative 3/2 times 2x plus the second function times the derivative of the first. The first function is x, that's derivative is 1. So the x squared plus 1 to the negative 1/2. All right, we'll clean this up well, the more you clean it up, the easier it makes the second portion. Here, the negative 1/2 and the 2 can be multiplied to negative 1. X times x is x squared. So we've got x squared over. This is negative 3/2 as a power. That's going to put it on the bottom. So it'll actually be the square root of x squared plus 1. Since it's to the 3/2, it's like saying squared and then times itself again. That makes simplifying it just a little bit easier. And then over here we just have 1 over the square root of x squared plus 1. In this left one, this left fraction, the square root squared right here, those can cancel. We really just have x squared plus 1 left. All right? So we'll do that. So we got x squared plus 1 should be absolute value, but since you're squaring and added 1 to it, it's guaranteed to be positive anyway. And then x squared of x squared plus 1 plus 1 over square root of x squared plus 1. So as we look at this, we got two fractions we're adding. We need a common denominator. Multiply top and bottom by x squared plus 1. And we can see when we simplify the top, x squared plus x squared will be 2x squared plus 1. And the bottom will be x squared plus 1 times the square root of x squared plus 1. From here, find our critical numbers for our second derivative. If you know anything about squaring a number and adding 1, that's pretty hard to get 0. If you square a number, it's guaranteed to be positive. If you add 1, it's guaranteed to be positive. The only number you can't square and get a positive number is 0. If you take 0 and add 1 to it, it's positive. So there's nothing that's going to make the bottom 0. There's nothing that makes the top 0. So again, we got no critical numbers for the second derivative. So everything is concave up or everything is concave down. And all we need to do is plug and chug and see positive or negative. And if I plug in 0, which is the easiest number in the history of mankind to multiply with, if I plug in 0, I'm going to see that 2 times 0 squared plus 1 is 1. 0 squared plus 1 is 1. I got one on top, one on bottom. It's positive. So this is always positive, so this is concave up on all real numbers. Or if we're going interval notation from negative infinity to infinity, and if you're asked the reason is the second derivative is positive. And on the AP exam, you're going to be asked a reason. And I always refer to the second derivative or the first derivative if you're talking about increasing, decreasing. And since it's always concave up or concave down, there are no inflection points. For number 14, let's find the extrema using the second derivative test. So first off, we need to find our critical values with the first derivative. So we'll find our first derivative. That would be 3x squared. 3x squared minus 18x plus 27. Looks like everything's a multiple of 3, so I'll factor that out. We got x squared minus 6x plus 9. That we can factor to x minus 3 squared. And we see we have a critical number at 3. And then we'll find our second derivative. All right. Instead of going back up to the original one, I'm going to use the chain rule down here. We get 6 times x minus 3. Power down, and the derivative of the inside is 1, so I don't have to do anything with it. If I plug 3 into that, second derivative at 3 is 0. So it is not an inflection point, or it is not a max or min. It may be an inflection point. All right. Since we're not asked for max or min, or we're not asked for inflection point, we don't really need to discuss it. However, we should, just because we haven't done one yet. So there's no max or min because the second derivative is 0 and the first derivative is 0. But I'm going to check to see if it is an inflection point, since there's second derivative is 0. All right, so what we're going to do, we'll make a sign chart again, and we're going to check left and right of our critical number, which is 3. Okay, if I substitute in 0, which is less than 3, I get 6 times negative 3, which is negative. So it's concave down to the left of 3. I go to the right of 3, I plug in a number bigger than 3, make it obvious, take like a billion. A billion minus 3 is positive. 6 times a positive number is positive. So 3, x equals 3, is indeed an inflection point. And you may be asked to find the y value, in which case you would just plug it in. So our inflection point at this point in time is 3 f of 3. And there is no max or min. What this looks like is your concave down going into it, concave up going out of it. There's your inflection point right there at the change in concavity where it kind of levels off. All right. The total cost for ordering and storing units is C equals 2x plus 3,000 over x. What order size will produce a minimum cost? Well, for minimum, you want to find where your derivative is equal to 0 and then do a check. Since this is on the second derivative test, we probably want to find the second derivative too. So let's find our first derivative. C prime is 2. Let's rewrite this as 2x plus 300,000 x to the negative 1. Our first derivative is 2 minus 300,000 x to the negative 2. We'll set that equal to 0. Okay, we'll solve for x. We got 300,000 over x squared equals 2. Multiply by x squared, divide by 2, take the square root. X equals the square root of 150,000. All right, that's our critical number where our max or min could occur. What we'll do here, we'll take our second derivative and we'll get 600,000. 2 is a constant. Negative 2 times negative 300,000. X to the negative 3. So our second derivative is 600,000 over x cubed if I plug in the square root of 150,000. And the reason why on this one I did not worry about negative 150,000 because x represents units. You can't store negative units. So if I substitute negative 150,000 into here, I'll get 600,000 over the square root of 150,000 units cubed. All I'm looking for is it as a minimum. And I can see the top's positive and the bottom's positive, so this is concave up. The first derivative is 0, it's concave up. Concave up like a cup, first derivative is 0. The minimum occurs at the square root of 150,000 units, which you can calculate out. The square root of 150,000 is about 387 units. So 387 units will produce a minimum cost. And so finally, in review, the first derivative test tells us where the function is increasing or decreasing. If the first derivative is positive, it's increasing. If the first derivative is negative, it's decreasing. All right, the second derivative test tells us concavity. If the second derivative is greater than 0, it's concave up. If the second derivative is less than 0, it's concave down. For a max or min, if the first derivative is equal to 0 and it's concave up, that's going to be a min. If the first derivative is equal to 0 and it's concave down, that's going to be a max. Because a frown has a top and a cup has a bottom. And an inflection point, that is where concavity changes. And to find any inflection points, you're going to find where the second derivative is equal to 0 or undefined, and just check the sign on left and right of those critical points.